session. Okay, so I hope you can see my screen, no? Can you see my screen? Can anyone please feedback? Okay. Okay, thank you. Okay, so so you know that we are doing RF modulation. Okay, we are still in RF modulation. Okay, so I think we have completed amplitude modulation. Okay, amplitude modulation we have completed. Okay, we have already completed, and we have to do another two modulation scheme. Actually, those are form of amplitude modulation, that is DSB, we call it C sometimes, and SSB. Okay, DSB, okay. DSB, SC, and SSB. DSB is dual sideband suppressed carrier. SSB means signal sideband. Okay, so these are form of amplitude modulation, and after that we have to do the phase modulation, and you have to do the frequency modulation. Okay, actually I forget in previous physical class we have done this too. Okay, in a physical session we have done this too, we have completed this too. Okay, and I have already uploaded the phase modulation lectures to the LMS. Okay, because now the time is not enough to do it like this. Okay, as an introduction session we can't do all these things. Okay, so I have uploaded I think 2 or 3 lectures there related with the phase modulation. Okay, so I have uploaded it. Actually today I hope to start the frequency modulation. Okay, but actually just now I could remember that this session, so some of you haven't participated for the physical lectures, no? So still you are not familiar with the DSB, SC, and SSB. Okay, so we will do like this. Okay, anyhow we have to cover these 3 schemes. Okay, so we have already covered this one, time domain analysis and frequency domain analysis. I hope you are now thorough with that part. Okay, and I think we have discussed this one also up to some level. Okay, in a physical interaction session. Okay, so we will try to do this too. Okay, maybe we need 1 hour, we can complete this too. Then after 1 hour we will start the phase modulation. Okay, frequency modulation, sorry, because phase modulation is already uploaded. Okay, so so we will do like this. Okay, so when you are referring the note, okay, I have properly number the lectures. Okay, the sequence of the lectures I have number part 1, part 2, part 3. Okay, when you refer the uploaded lecture, please go through that sequence. Okay, then you will not get any confused. Okay, so we will start. Okay, so actually this is we have already discussed this one. I think you can remember that. Okay, in a physical interaction session we have discussed what is this DSB. Okay, so so I think we have calculated so if we take the AM modulated signal. Okay, AM modulated signal, Okay. So a modulated means, okay, we have a carrier. Okay. We have a carrier signal. Okay. Sine, sorry, cos omega ct like this. Okay. And we have modulating signal or information signal that is empty. Okay. So for simplicity, uh, considered a single tone signal. Okay, that means one sinusoidal signal. Okay, so our information signal will be like this. Okay, so this will be AC cos omega ct. So it is like a cos omega mt like this. Okay, so this is our information signal. It is a single tone signal. Okay, it is a single tone signal. Okay, only one tone is there, and this is our carrier signal. Okay, so output is the amplitude modulated signal. Okay, so we have we can write the amplitude modulated signal. Okay, let's see it as XMP. Okay, so this is the modulated signal. Okay, so we get it like this. I think you can remember that one. Okay, one mu mu I will write as m divided by AC. Okay, and cos omega mt. Okay, and and uh, and cos omega ct. Okay, so this is the modulated signal. Okay, so we have already know this one. Okay, and if we have so using some trigonometric identities, we can expand this signal. Okay, we can expand this signal and we can write this signal like this. AC cos omega ct plus, I think you can remember these things. Okay, AM divided by 2 cos omega c omega mt plus AM divided by 2 cos omega c plus omega mt. No? So we can write this like this. Okay, so we can write our modulated signal like this. Okay, actually we use some basic trigonometric identities. Okay, I think you can remember how to write them. Okay, so we can draw the spectrum of the signal using this waveform. Okay, so we have three frequency component, this one, and this one. Okay, so one frequency component is omega c. Okay, the amplitude is AC. Okay, and this frequency component is omega c minus omega m, and this frequency component is omega c plus omega m. Okay, and this is AM divided by 2 and AM divided by 2. Okay, so these are the frequency component. Okay, and I think so this is the amplitude modulated signal, AM signal. Okay, AM waveform. Okay, for single tone, for one tone. Okay, we have already modeled. And so if you consider so if you put some voltage values, so amplitude levels to AC and AM, okay, so you know that to have a proper modulation index, AC should be greater than AM. This is a condition. No? Otherwise, we will our modulated signal will be distorted. We have already learned these things. Okay, so if I assign some value to this AC and AM, okay, let's say that AC is 100 volt, okay, and AM is 10 volt something, okay. So if I ask you to calculate the power of these three components, okay, of these three components, I think you can calculate the power, okay. So these are the frequency component, okay. And the power is nothing but the square of amplitude divided by 2. We have already seen that one also, okay. So the carrier power will be AC square divided by 2. That means 5,000 watt, 5,000 watt, okay. And so these are these we called actually sideband, okay. So these are sideband, okay. These are sideband, okay. And if I um, find the power of the sideband, okay, power of the sideband, power of sideband. So the two sideband has the same power, no, have the same power, okay. So it will be AM square divided by 2, okay. So it will be 100 divided by 8, okay. Okay, so this is the carrier power and this is the sideband power, okay. So you can see that, okay, we have already seen these things, okay, in our physical interaction session, okay. So you can see that the carrier power is very high and the sideband's power are very low. And also, if we look at the spectrum, you can see that this carrier component, okay, this carrier component doesn't have any information signal. It doesn't have any information signal. Okay, it doesn't have any information signal. But the sideband have the information signal, no? Omega M and omega M. Okay, so this has the information signal, but this carrier component doesn't have any information signal. Okay, so and also you can see that that carrier doesn't have any information signal, but it has very high power, no? Okay, so if you are transmitting the total spectrum, you can see that we have to use a very high transmitting power. Okay, so that is not good. Okay, so somehow if we can remove this carrier component, okay, if you can remove this carrier component somehow, okay, then you have only these sidebands, and that band also have the information signals, no? Okay, so at the receiver, maybe you can properly extract the information signal using very low transmitting power. Okay, so very transmitting power means your transmit and receiver doesn't use much power. Okay, so if you are using a battery to the transmit and receiver for as a power supply, then your battery life will be high. Okay, so you have a long battery life. Okay, so if you are reducing transmitting and receiving power, your battery life will be long. Okay, so that is an advantage, no? So we can, if we can somehow reduce this AC, okay, information signal, so you can see that we can reduce the transmitted power as well as we can extract the information signal. So our uh, so our task is happen. Okay, so our task is achieved, our aim is achieved with the low power. Okay, so now the problem is that how to suppress this carrier. Okay, so I think you have given some uh, solution for that one. Okay, so some of student has proposed a band pass filter. Okay, band pass filter to filter this component. Okay, to filter this component. Okay, Actually it is a good approach, okay, but sometime uh, that will cause some other issues. Okay, if you use a band pass filter, what happen is that, okay, so here if you are using a band pass filter, okay, so here if you are using a band pass filter, here you are using a band pass filter, okay, then what happened? Uh, your carrier signal will be removed, maybe, okay, or you can see maybe you can use a low pass filter also, okay, because the carrier frequency is high and the modulating frequency is low, okay. So if you use a low pass filter, maybe this high pass frequency will be cut off and you will have the low pass signals, okay. That means this carrier component will be suppressed, okay, but the problem is that, okay, so if you look at this one, okay, so this has the carrier component, this also has some carrier frequency, this also has some carrier frequency, okay, so these are also maybe high frequency, okay, these are also maybe high frequency, okay. So if you remove the carrier component using a band pass filter or low pass filter, then this carrier component can be removed, okay. Then at the output you will not have a modulated signal, okay, you will have only the information signal here. So sometime you will have the information signal only. Our information signal is same cos omega mt. Okay, maybe you will have this one. Okay, because all the carrier component will be removed. Okay, in this one, and this one carrier component will be removed. Okay, so finally maybe you will have only a information signal. So modulation is not. So if you are using a filter here, the modulation waveform will be affected. Okay, so that approach is not proper actually. Okay, so we have to use another approach. Okay, so we can use what is called balance modulator. Okay, so one approach is there. Okay, that is called balance modulator. Okay, balance modulator. Okay, then using the balance modulator, you can suppress the carrier signal. Okay. Okay. Actually, this is the balance modulator. Okay, this is the balance modulator. Okay, so you can see that here you have two AM modulators. Two AM modulators. Okay, so here you have the signal, and here you have minus signal. Okay, so this is minus signal. Okay, so actually, if you have done the signal and system, okay, so this is we have learned this one. Okay, we have learned this one, this minus part. Okay, actually this is called amplitude reversal. Okay, this is called amplitude reversal. Okay, so you can use the electronic circuit to do this amplitude reversal. Okay, so you can, if you have a message signal, you can multiply it by -1 and you can give a minus signal here. Okay, and you are giving the same carrier frequencies to the AM modulator. Okay, and here you can see that you have a signal ladder. Okay, so this is a signal ladder. Okay, so signal ladder also there are many type of signal ladders we can implement using electronics. Okay, summing junctions are there, signal summing junctions are there, and also the summing amplifiers are also there. Okay, so you can use this, you can implement this adder, signal adder in electronics. Okay, very easily. Okay, so you can Google it and check what are the methods. Okay, and you can see that. So here you have a modulated waveform because it is going through a modulated signal, and here also you are using modulated waveform. Okay. And this is the modulated waveform. Here you are also doing the AM modulation, and this is the modulated waveform. And you can see that this modulated signal, it is a 1, okay, it's 1T, okay. And this modulated signal, it is multiplied by minus. Again, it is amplitude reversal, okay. So here you have minus S2, okay. So ST, you will have S1T, this is plus and this is minus S2T. Okay, so this is the output signal. Okay, here. Okay, now, okay, try to get expression to ST, that is this output signal. Okay, so what you have to do that? Okay, it is very easy. You have to write the amplitude modulated waveform here, and you have the amplitude modulated waveform here. And if you subtract this waveform from this one, you will get the ST signal. Okay, so try to get the expression for that one. Actually, this is the balance modulator. Okay, so we will see how it happened. Okay, so first try to get the expression for this ST. I think you can get it using your amplitude modulation knowledge. You can get the expression for this ST. Okay, what you have to do that, you have to find this 1T and you have to find this 2T and subtract. Okay, so try to do that one. So I will give you 10 minutes. Okay, so can you see my screen and can you see my writing? I hope you can see, no? Okay, so what you have to do then? Okay, first you have to write the expression for S1T. Okay, so that is the modulated signal. Okay, a modulated signal. Okay, so it is very easy. You can write it. Okay, 1 plus MT. Okay, so you can say that MT has the amplitude. No, this MT should have the amplitude in it. Okay, so this should be divided by AC. Okay. So I think it is clear for you now, okay? And this is cos 25FC, okay? And what is S2T? That is AC 1 plus MT. So, sorry, here it is minus, no? Here it is minus. Minus cos 25FC. Okay, and what you have to do? You have to reduce this, no? You have to subtract S2 from S1 because S2 again you are amplitude reversal. This S2, okay? So it will be minus one. And you are adding them means you have to subtract. Okay, so ST is, so if you subtract this one from this one, this one from this one, this cos 25 FCT, cos 5 FCT is cancelled out. Okay, and AC you will have MT divided by AC cos 5 FCT. Okay, correct? Okay. So this is the waveform you get, no? Is it correct or wrong? Can anyone tell? This is correct. Is this correct? ST? Can someone feedback? Is this correct or not? You can hear me, no? Please give me a give me a feedback to proceed, okay? Otherwise, the time will be not enough. Please give me a feedback to proceed. Yeah, thank you for the feedback. Okay. Actually, this AC part is not needed here. No? This one no need here. Because this AC multiplied by this empty AC cancel out, and you will have empty cos 25 FC T minus empty cos 25 FCT. That means empty cos 25 FT plus empty cos 25 FT. So you will have this. Okay. 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 Thank you for your feedback. Okay. So this is the correct one. Okay. Okay. So 2 empty cos 25 FCT. Okay. So this is the. So so this is a balance modulator. Okay. So the output of the balance modulator. Okay. This carrier should be suppressed. Okay. This carrier part should be suppressed. Okay. And you will have only these two side band. Okay. Only these two side band. Okay. So we called it. Okay. We called it dual side band carrier suppress. Okay. Because we have suppressed the carrier, we have eliminated the carrier frequency, carrier component, and we have only two side band. Okay. Okay. Now, by looking at this, okay, so this is the DSB-SC waveform, DSB-CS waveform. Okay. This is called SC. Okay. DSB-SC, suppressed carrier. Suppressed carrier. Okay. So so this is the DSB-SC waveform. Okay. So this is not the AM waveform. Okay. So you can see that if you consider this one, okay, if you consider this one, actually this part is not here. Okay. This part is not here. You will have only these two. Okay. For this one, you will have this 6 2. I think if you can remember that basic trigonometric identity, you can understand that one. Okay. So you have two basic trigonometric identity. Okay. That is okay. I will come to that part. Okay. I will come to that part. Okay. Okay. Now, maybe by looking at, so you can see that. Okay. So you can see that here you will have the carrier frequency. No? Here you will have the carrier frequency, and here you will have the information signal, and those are multiplied. Okay. So those are multiplied actually. The carrier and information signals are multiplied together, and it is and you get the twice of that. Okay. So that is the DSB-SC output. Okay. So sometimes you see that you may feel that here we have the carrier component. No? Here you have the carrier component. So it is the carrier part is not suppressed. Okay. Actually, that is not true, because this will generate two frequencies. Okay. Two separate frequencies. You already know that if two frequencies are multiplied, okay, it will generate another frequency. No? Another frequency component. Okay. Not the same frequency component. We have already seen it in MATLAB. Okay. Okay. So maybe you couldn't understand that one. Okay. Now I will give you another example. Okay. Another example. Okay. Now consider this MT as, let's say that AM cos omega MT. Okay. So now So this is the DSP-SC modulated signal. Now you have to consider this MT as AM cos omega MT. Okay. So this is a single tone. This is a single tone information signal. Okay. So actually this is a single tone. Okay. Now you are going to find the waveform. Okay. Now you are going to find the waveform for DSB SC, dual sideband suppressed carrier modulation for single tone. Okay, for single tone signal. Okay, so your input signal, your modulating signal or your information signal is one tone signal. Okay, now can you try to find the ST? Okay, so let's say that it is a single tone ST, SST. Okay, your single tone modulated signal, that is true. Okay, now AM cos omega MT, the carrier signal amplitude is not here, only the carrier signal is here, cos 2, 5. Okay, so I will write this 2, 5 FC as omega C. Okay, this 2, 5 FC as omega C. 2, 5 FC is equal to omega C for simplicity. Okay, so here you have omega CT. Okay, so this is the single tone DSB-SC waveform. Okay, okay. Now try to find the frequency component here. Now you have to find the frequency component of this signal. Okay, so you can see that we have a multiplication here. Okay, so if you have a multiplication, you can't identify the frequency component. What you have to do, that you have to convert this multiplication to a addition. Okay, multiplication to addition, then you can find the different frequency component. Okay, so that is the normal way we used. Okay, and if you have done the Fourier analysis, you can get the Fourier transform. Okay, then also you can find the frequency component. Okay, if you get the frequency Fourier transform of this signal, okay, you can get the frequency component. Okay, or otherwise, okay, so some of you haven't done the Fourier series analysis, no? Okay, so you can use that basic trigonometric identities, and you can convert this multiplication to addition. Okay, so what is the trigonometric identities we are using here? Can you remember that? So you have cos omega m, cos omega c. So it is just like cos alpha, cos beta term. Okay, cos alpha, cos beta term. No? Okay, so where, in which trigonometric identities you found these two terms? Okay, so you already know that. Okay, that is sine. Correct? No, cos. No, not sine, cos. Okay, that is cos alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta. Okay, and cos alpha minus beta is equal to cos alpha cos beta plus sin alpha sin beta. So these two trigonometric and identities you have to use. Okay, then find the frequency component here. Okay, what are the frequency component? Can anyone feedback? I think very easy. You have already know this. Okay, how to apply this. So what is the frequency component? What are the frequency component? It is very easy. I think within 2 minutes you can give the answer. What are the frequency component? Okay, thank you. That is the correct answer. Okay. So I am not going to resolve this because we have already done this. Okay. In amplitude modulation also we are doing this calculation. Okay. So you will have, okay, you will have, so what you have you have to do is you have to add these two. Okay. Then cos alpha plus beta, cos alpha minus cos beta, you will have 2 cos alpha cos beta value. Okay, so here the same value is there. Okay, so you will have am cos alpha plus beta. Okay, so that is omega m plus omega ct plus no plus am cos omega alpha minus omega beta. Cos alpha minus beta, that means omega c minus omega a. Okay, so this is one frequency component and this is one frequency component. Okay, so this is the spectrum. Okay, so if you have draw the spectrum, okay, if you have draw the spectrum, okay, with respect to frequency omega c, okay, now you have one band and you have another frequency component. Okay, and here you have am and here also you have am. Okay, so what is that? Here you don't have the carrier component. No, here you don't have the carrier component. Okay, so it is suppressed. Okay, so you can see that it is suppressed. This carrier component is suppressed. Okay, it is eliminated. Okay, so you will have this kind of spectrum. Okay, so if you are using a spectrum analyzer to show this waveform, okay, so your amplitude modulation should be like this. Okay, your amplitude modulation waveform, the spectrum should be like this. Okay, this one, it is not this kind of impulse. Okay, so you will have this kind of bell-shaped curve for the spectrum. Okay, and for the DSBSC, you have only these two. No, you will have this kind of, actually we have seen this in our labs, no, but this is not completely suppressed. Okay, the carrier part is not completely suppressed and you will get this kind of okay. So anyway, this is the DSBSC modulated waveform and the spectrum. Okay, so you can see that the carrier is suppressed and you have only these two side bands. Okay, you have only these two side bands. Okay, you have only these two sides. Okay, so that is it. Okay, so if you want to get the same, so you can see that here amplitude is am by divided by 2, but the amplitude is here am. Okay, but if you need to get the same amplitude, okay, what you have to do, you can get the half of this signal. Okay, half of this signal and you can send. Okay, so you will get exactly same spectrum without the carrier component. Okay, so that is DSBSC. Okay, and okay, and now, okay, now you can see that, okay, now you can see then, okay, Okay. So here you have only two sideband. Okay. Here you have only two sideband. Okay. Sideband. Okay. That means this sideband and this sideband you will have. Okay. So if you are transmitting this two sideband, okay. So this is the power for one sideband. Okay. And if you are transmitting this two sideband, you will have twice this sideband power. No? Sideband power. That means twice of this power. Okay. So that is clear. Okay. So you can see that in this sideband also you will have the information component, and in this sidebands also you will have the information component. Okay? And if you have sent one sideband only, okay, one sideband only, that is also maybe enough to recover the information signal. Okay. So here you are sending two sideband. Okay. And you have to use double power. Okay. 100 divided by 8 watt. Okay. 100 divided by 4 watt, that is 25 watt. Okay. So you are using 25 watt. Okay. And but if you can somehow eliminate this one sideband, okay, this power will be again reduced to half. No, it will be 20.5 watt. Okay. So you can further save the power. Okay. If you are sending only one sideband, you can further save in the power. Okay. So that is called signal sideband modulation. Okay. So here, okay, here you are sending two sideband. Okay. And if you are sending one sideband, okay, one sideband only, that is signal sideband modulation. Okay. So you can further save your power. Okay. So how to get one band from here? You have two band. Okay. Now you have two band. Okay. And how to get one band here? Actually, here now you can use a filter. At this point, you can use a filter. Okay. You can use a filter. Okay. So that filter should be maybe a band pass filter or band stop filter. Okay. So let's say that if you are using WC minus WM band pass filter. Okay. So this is the lower frequency or low pass filter. Okay. So you will have only this component. Okay. You will have only this component. Okay. And the carrier will not eliminate, no, because you are not using the carrier. You are not going to filter the carrier component. Okay. You are going to filter this one, omega C plus omega M part. This part. Okay. You are going to filter this one. Okay. Okay. So it is not a carrier component. The carrier frequency associate with that part. Okay. But that is not the pure carrier component. No? Okay. So this will be saved. Okay. This will be saved. Okay. So you can cancel out this one using a band pass filter or band stop filter or low pass filter. Okay. And you can get only this part. Okay. And also you can use a high pass filter or band pass filter related with omega C plus omega M. Then you can only transmit in lower sideband. Okay, lower sideband, that is omega C minus omega M. Okay. So using here you can use a filter. Okay. So you are using a filter to eliminate this filter. You are using to eliminate, okay, omega C minus omega M band frequency of omega C plus omega M frequency. Okay. This filter you are using to eliminate this one or this one. Okay. Then you are not going to eliminate the carrier frequency. But here, if you are use the filter and you design that filter to eliminate the carrier component, omega C, again you will have the information signal only, not the carrier components are there. These carrier component also may be cancelled out. Okay. But here this, now you are using a filter not to eliminate the carrier component, but to eliminate this frequency or this frequency. So these are two different frequencies. Okay, it is not same as the carrier. Okay, so that is it. Okay, so that is how we can eliminate using a filter. You can implement the SSB waveform. Okay, okay. Now we will so we will stop our